Start recording. Okay. Good afternoon, everyone, and let's start our lesson. Well, today I want to do a problem. Well, if you remember, we have started solving this problem, and I asked you to solve this by yourself. Okay. Have you done this problem or not? Do you have questions, or maybe you didn't understand something in this problem? Okay. Have you solved this problem or not? Just say yes or no. Okay. Okay. And do you have any questions regarding this problem? Well, please ask, don't hesitate if you have questions regarding the problems. In any case, you have to solve all the problems, because at least you have to pass the exam. Well, it seems that you don't have problems with this exercise. Let's move on. Okay, we have another problem. It is saying two trains approach each other at velocities v1 and v2 as shown in figure. Okay, assume the train's axles are good conductors and rails have a resistance R ohm per kilometer. Okay, use D equal to 2 meters. The trains are P equal to 10 kilometer apart. Also, given that V1 is 100 km per hour, V2 is 120 km per hour, R is 0.1 ohm per kilometer. Okay. The vertical component of terrestrial magnetic flux density B0 is 0.05 millitesla. We need to calculate the current in the rails produced by the motion of the trains in the terrestrial magnetic flux density at the instant shown in figure. Also, the current in the rails as a function of time, taking t equals 0 at instance shown in figure 1037. Okay. What are the given data? We are given V1 as 100 kilometers per hour. V2 is 120 kilometers per hour. Okay, first of all, we need to convert this to units of measurement. We need to convert to SI, units of measurement. 100 kilometer per hour is equal to 100 divided by 27.6, 27, 27.8 meter per second, and 120 is 33.3 meter per second. Okay, and the vertical component of terrestrial magnetic flux density is B0, 0.05 millitesla, which is 5 multiplied 10 to the minus 5 Tesla. Okay. Well, first of all, we need to compute the current in the rails as a function of time. So, A. Now, we need to compute current. Okay, current is equal to electric motive force divided by the resistance. And which is in turn electric motive force by the definition is equal to the integral over the closed path C V cross B dl, and we can divide our this is the closed path which is given in our problem. We can divide this into 4 parts. Part 1, which is this, and part 2, part 3, and part 4, and we can write this as electric motive force of the part 1 plus electric let me write here electric motive force 1 of the part 1, electric motive force of the part 2 plus electric motive force of the part 3 plus electric motive force of the part 4. So if we look to our problem, part 2 and part 4 are the stationary rails. It means the velocity of the part 2 and velocity of the part 4 are 0. Just rails are just laying without movement. It means that electric motive force of the part 2 is 0. Electric motive force of the part 4 is also 0. And for electric motive force 1, we have integral over the, okay, let me write 1 over the first part, V cross B, in this case V1 cross B dl plus integral over the third part, in this case V2 cross B dl, and this everything equals to okay. Well, let me move here and let me move this here. And first integral, this integral gives us in the previous lessons we have already derived the results of these integrals. Okay, first integral gives us v1 b0 d, and second integral gives us v2 b0 d, or v1 plus v2 b0 by d. And if we put numeric values, v1 was equal to 27.8 plus v2 was equal 33.3. Multiplied by b0 was 5 to the 10 to the power minus 5 multiplied, and d was 2 meters 2. And if we compute this 27.8 plus 33.3 is 61 multiplied by 5, well, 61 multiplied 5 multiplied 2, okay, 6.1 10 to minus 3 volts, or 6.1 millivolts. The electric motive force occurring in our system due to the motion of two trains is equal to 6.1 millivolts. Now, we know the electric motive force. In order to compute, look here, in order to compute the current, we need to compute the resistance in our system. So if we look one more time to our picture, it is saying assume that trains axles are good conductors. It means this part and this part of our circuit has no resistance, and rails have resistance of R, which is equal to 0.1 ohm per kilometer, and the distance between two trains at the beginning of our problem is 10 kilometer. Now, okay, in order to compute the resistance R, we have to, so R, let me write R1, which is the resistance of one rail. R1 is equal to P multiplied by R. P is 10 kilometers. It means 10 multiplied 10 to the 3. Look, in this case, we may not convert the units, because if we write 10 kilometers multiplied, R is given as ohm per kilometer, 0.1 ohm per kilometer, and kilometer simplifies with kilometer and remains only ohm. Resistance of one rail is equal to 1 ohm at the very beginning of the motion of trains, and the total resistance is twice the resistance of one rail, because we have two rails, and is equal to 2 ohm. And current I will be equal to electric motive force over the R. So electric motive force was 6.1 10 to the minus 3 volts over 2 ohm. This is equal to 3.05 10 to the minus 3 amperes. So the current which flow at the beginning of the motion of trains is equal to 3 milliampere. Now let's switch to the second part of our problem. In the second part is saying calculate the current in the rails as a function of time, taking t equals 0 at the instance shown in figure 10.37. Okay, we need to compute B I T. So I of time will be equal to, well, electric motive force doesn't change with time, because the trains are moving at constant speed. However, the resistance of our system will change with time, because the so-called active length of rails is reducing with time. Now, let's compute RT. RT is equal to some value of R0 minus R multiplied by V, or let me write R multiplied by LT yeah, and we don't know this constant R0, and okay, we can write this R multiplied LT, but we don't know the constant R0. So if we go to our problem, it is saying that taking that t equals 0 at the instance shown in figure 10. So the initial condition, uh, is r t equals 0 is equal to r0, which is the resistance of our rails at the beginning of the motion, which is r multiplied by p multiplied by 2. So we have already computed this. It was 2 ohm. Okay. Now let's compute R multiplied LT. Let's compute the resistance, change of resistance with respect to time. Okay. R multiplied by LT is equal to R multiplied by V by time T. Okay, here V is sum of V1 plus V2 T, and is equal to R is 0.1 ohm per kilometer. Now we need to switch to SI units in order not to make a confusion. So R is 0.1 okay, ohm per kilometer, or 10 to the minus 4 ohm per meter, and okay, V1 plus V2 we have already computed. It was 61 meters per second. Okay, now we may write the equation of current with respect to time. Okay. Tak. Okay. So I don't need this. I don't need this. So I move it here. Okay. Now the resistance with respect to time is equal here R0, which is 2, minus R multiplied LT. R is 10 to minus 4 multiplied L is LT is 61 T, or okay, if we simplify a little bit, we get RT, which is equal to 2 minus 6.1 10 to minus 3 T. And now the current with respect to time is equal to electric motive force over RT. Electric motive force was equal to, so electric motive force was equal to 6.1 10 to minus 3. 6.1 10 to minus 3 over RT is 2 minus 6.1, okay, 10 to minus 3t. Okay, this is the equation of the current with respect to time. Okay. Well, do you have questions or any misunderstandings regarding this problem? Okay, no questions. Great, no questions, no understanding. Okay. Mm-hmm. So, next. Well, next we'll speak a little bit about some applications of Faraday's law. There are several applications. We have already seen the application of eddy currents. Well, one another application is a homopolar generator. Homopolar generator. And we have already seen that if we have a conducting bar moving at some speed, conducting bar moving at some speed in a uniform magnetic field, it produces the it produces DC electric motive force. Well, one application of this phenomenon is DC generator. In this case, we don't have. Okay, in this case, we don't have a moving bar. Instead of moving, we fix our bar at some point and we start to rotate it with some angular frequency of omega. This gives us the same effect as the moving bar, and it produces DC current if we connect if we connect to the ends of our bar. Well, the connection to the ends of our bar maybe sometimes not so easy, and instead of connecting to the moving bar, we can use the structure which is shown in this figure. We have a stationary ring, conducting ring, inside which our bar is rotating and one end of our bar is sliding inside the conducting inside our conducting ring. Okay, our ring stays stationary, and if bar rotates at some frequency, we have the induced electric motive force with DC current. Okay, the opposite application of this phenomenon can be seen in DC motors. Well, instead of rotating bar around some axis, if we apply this is our disk. If we apply some voltage to the to the end of disk and to the center of disk, here occurs some imaginary bar, and current starts to move in this direction, and because of the movement of currents there occurs force acting to this part of bar, and this force makes disk to rotate, and this can be a very simple working principle of DC motors. Okay, here is written that this is again the generator, but the DC motors work in the same principle. We can here you can see. Yes, here I have shown that current will go through the disk in this direction. Okay, here you can see it is shown when we apply some voltage to the axis of disk and to one end of disk, current will start to move, and because of moving current there occurs force acting to the current. Okay. Well, you have 3 more minutes. If you have questions, please Please ask. Well, it seems that everything is clear to you, or nothing is clear because of no questions. Okay. Well, so experiments, transformer.
Ustoz,
Yep.
shu kitobni tashlaganmisiz?
I think yes. It should
Sal
be.
boshqacharoq bo'lar ekanda bu yerda.
Yes, it is. Yes, this is a bit different. This book seems to be more easy and more practical. That's why
Tashlab yuborsangiz bo'lar ekanda bu.
okay, I will upload this book also to the Moodle or to the Telegram channel.
Telegram channel. Wow.
Okay.
Then
Well, are you doing some problems by yourself or not? Well, look, what about this problem?
hozircha
What about this problem? We have started doing this problem in previous lessons, but we didn't finish. Have you finished this problem at home or not? Well, it seems to be
no kecha
okay. We will try to do this problem now after. Okay. Well, so far, if you don't have questions, have a rest, maybe 10 minutes. After that, we will continue. First of all, we will continue with this problem, and after we will see another applications. Okay.